Umberto held a series of postdoctoral positions, including in the UK, including Keele University, University of Edinburgh, University of Hull, where he worked on stellar evolution, nuclear reaction networks, and the chemical evolution of the galaxies. His research interests center on the cosmic origin of the elements, type 1a supernova progenitors, stellar explosion, and the connection between nuclear physics, stellar modeling, and gamma ray astronomy. Today, he will present the topic on heavy elements exclude to the progenitors of type 1a supernova. Okay, I leave the floor to Umberto.
Thank you, Chiara. So thanks, everyone. Nice to be here. And so, yeah, just as a first thing first, just want to show you more or less like a part of the key collaborators, at least for the work I'm going to present today, which is understood like encompass like a number of individuals from primarily the UK, where I spent but a huge part of my career so far, plus other key actors from Germany, from other parts of Europe. So it's a nice international effort, and then culminating the recent publication of a work which also involved Luciano and Oscar and other researchers here at Teramo, and I hope you enjoy the presentation. So I'd like to start, yeah, so giving like a brief additional like overview of what I'm actually doing, so what's my field of research. So I'm mostly interested in the study of the stellar life cycle. More precisely, most of my research really focus on the low end of the initial mass regime of single stars primarily, but also, of course, in the product of binary system evolution, primarily the evolution of what happens if you have a white dwarf, so the compact remnant of a loma star's evolution when there's a companion, and so especially on which condition leads to the triggering of the supernova. I also spent some time in the massive star regime, but in that case primarily from a synthetic point of view rather than the catastrophic evolution, but more or less that's what we are talking about. Of course, I'm also very keen about what's the legacy of the life of all these objects in terms of nucleosynthetic elements, and what's the wider relevance of the work I work in. Of course, no one today is isolated in his own field, so my job is quite relevant. For example, the output I produce can be, in terms of ejected amount of chemical elements, can be incorporated into a GC code, galactic chemical evolution code, in order to reproduce the gradual enrichment of the galaxy into heavy element, in order to reduce in particular the evolution of the chemical species as a function of time, or using as a proxy metallicity. Reproduction is another big chunk of what I'm doing, and of course also working quite in close contact with nuclear physics, like for example people working at SASO in the Luna collaboration, of which I'm part, and top at CERN, performing nuclear sensitivity studies with a tool I have developed and maintained within, in my case, within nuclear collaboration. As talking about, today we're talking more about type 1a progenitor, and I also want to introduce more or less the pipeline that I'm inserting in the context of the collaboration I'm inserting. So I want to, well, this pipeline, I call it, it's not an official name, I call it thermohydrodelphast pipeline, more or less. It starts from here. It's like a sequence of steps. It starts with a progenitor model of what can really be at the origin of type 1a supernova. From project, you simulate what happens before the explosion. Then you simulate the explosion, which of course heavily depends on initial conditions, which are set here. Then from the atom explosion, you can be a post-processing step. So using the temperature and density history that are the results of this step, you can use it to compute nucleosynthesis in a full network approach in a post-processing step. This gives you all the chemical elements produced during the explosive nucleosynthesis, which then can be used to provide the so-called radical simulation, which the main target is to to compute synthetic observables, so to predict what can be observed out of all this stuff in terms of absorption line, for example. And this can be used as a prediction for observational data. So I'm mostly involved here. Notice that sometimes this step is kind of skipped. Sometimes just initial guess is made, assuming like a certain white dwarf with a certain structure and some decomposition. I am to consider this simulate progenitor phase. Also, I'm really keen in what happens in the external layer, where very interesting things can happen in terms of nucleosynthesis, which in many cases neglected. This step is under the is driven by the Heidegger group, like with the guidance of Röpke. Then I appear again here sometimes. Sometimes this step is, or sometimes it's taken by Hall, by James Deegan, sometimes in Heidelberg as well by Alexander Olas. Then everything passed to Belfast under Stuart Sim, which was here visiting us just before Christmas. And then, well, hopefully all the results we get here will be quite interesting for the observational community. And it's a good time because really huge and extensive observational campaigns are about to start. For example, LSST or formal studies are the two I'm personally really looking forward to. Okay, so just after this like introduction, let's dive into the type 1A business. So what we care, for example. So, well, type 1A supernova are really key events in the universe. From a galactic evolution point of view, just think about that. More or less 2/3 of the iron content in the Milky Way was produced by specifically the explosion of this kind of stars, with the remaining third coming from the explosion of massive stars instead. A minimal fraction of P nuclei of this really interesting nuclei beyond iron on the bottom left side can come from here. They're not many, but they're very interesting. They carry a lot of stories in them. Also, why we care about iron? Well, number one is one of the most abundant elements in the galaxy, but it's also crucial ingredient for planetary magnetic generation. So it's really connected, important to the field of astrobiology, for example. So really key to make a planet habitable in terms of genetic magnetic field, able to deflect the stellar winds around which it is orbiting, but also for the formation of protein enzymes, by the way. It's quite a key element. So really played a central role in the measures of life, as you know, on Earth. Additionally, as you may know, due to their characteristic light curve, type 1A are also standardizable candles for cosmic distance measurement, and this led to the discovery of key evidence for the accelerated expansion of the universe, which eventually led to the Nobel Prize in Physics in 2011. And so there's really important events, really key, and yet the nature of the type 1A progenitor is really still a matter of debate. There are many reasons for that. Number one is really hard, if not impossible, to observe a white just before the explosion because they are so dim, often so distant. So what you can do is watching the explosion, and as I hope to make understand, what I hope to do with my work is to find some distinct observables in the emission of this explosion that can be uniquely linked to a specific kind of object. Hopefully that's my goal, and see if it is feasible, of course. So type 1A progenitor, why is so complex? Is such a complex issue? Well, another reason for that is that there's a huge variety of possibilities that can lead to the explosion. There's not just one or two scenarios. There are quite a few. I just show you. I try to organize organize them into some consistent subclasses. So I think one of the most effective way to talk about type 1A progenitors is to divide them into near Chandrasekhar mass event and sub-Chandrasekhar mass event. What the Chandrasekhar mass is basically the highest mass that can be sustained by this called electrostatic pressure, above which basically the stuff is not stable. You have a collapse, and And for carbon, that's depending on the composition. And for the composition of mostly carbon oxygen, it's around 139 solar mass or something like that, depending on the details of matter physics involved, of course. So both these classes, both Chandrasekhar mass event and sub-Chandrasekhar mass event, can be achieved in two ways, either via a single degenerate fashion. So when you have a single wire system, accreting material from a less stable companion, which still has an envelope around it, or in the so-called double degenerate scenario, when you have two degenerate objects, or so two wires with one another, and leading to some sort of interaction. So when you have in the case of each and the second mass event, through the single degenerate case, that's mostly the case of hydrogen accretion events. So when you have a wire dwarf accreting a hydrogen-rich envelope from a companion, so a white dwarf star and a companion which is not that old yet in terms of evolutionary time, so it still has its hydrogen envelope around it. When this star evolves, it goes through at the end of the main sequence, goes through the right giant phase, giant branch phase, eventually filling up the slope and establishing a mass transfer. So you can imagine that the mass transfer sets up, the hydrogen envelope starts to be accreted on top of the white dwarf, some nuclear processes takes place, converting into carbon oxygen, and eventually somehow it's possible to reach Chandrasekhar mass. Now, how efficient is this path to trigger type 1a? Well, there are some observational data that tells us that this is not really the easiest way to get there. Looks like, according to Johansson et al. In 2016, looks like that just a few percent of the total type 1a array can really originate from this channel here. So the hydrogen accretion from the companion. There's another way to get into a neutral second mass event, which can be in a double degenerate fashion, which involves the slow merger of two wire dwarfs via the formation of an accretion disk. So basically, you have the two wire dwarfs. If the mass is not too similar, so the mass ratio is below about 0.8, something like that, the less massive water will be kind of disrupted by the primary. You form an accretion disk, and you can actually establish a slow accretion from the accretion disk. In this way, you can increase the mass of the primary until you reach the Chandrasekhar mass. What about sub-Chandrasekhar mass event? These are really important, more than we thought 20 years ago, something like that. We can have sub-Chandrasekhar mass event in a single degenerate fashion when you are creating helium-rich material from a companion. In this case, what happens is that when you build up like a critical mass of helium on top of the one of the order of some tenth of solar masses, you ignite explosively the helium on the surface, propagating a shock, a detonation wave to the center, which ignites the carbon and ignites an explosion. This is called double detonation scenario, and today it looks like one of them. It looks like to be capable of producing the majority of the type 1 events out there. Looks like that quite possibly between 60 or 70% of the type 1A can come from this channel, but we still need, in terms of galactic evolution constant, especially if you try to reproduce the titanium vanadium evolution in the galaxy, you still need at least a fraction, 40–30% of near Chandrasekhar mass event. This is because if you just do your computation simulation, assuming 100% of type 1A, even of standard type 1A from this channel here, you tend to overproduce these two elements compared to one. So you need something that produces more iron to keep it down. There's another chance, another way to get to sub-Chandra explosion, which is through violent merger, which is and this can come when you have two wire dwarfs or similar mass. So in this case, you have you don't have one wire dwarf getting finally distracted. You have a violent merger event and the prompt detonation during the merger process, especially if helium is present. Okay, so you see how there's quite a lot of possibility to get there. But the key point is, we still need like you still need a fraction of both. Like we likely have a situation where there's a dominant channel, and this is likely this case here, but you still need a chunk of events coming from this side, and that's what I'm focusing in this presentation. So in this work, really, we are focusing on this channel here, on the formation of near Chandrasekhar mass event from this part. So because the reason is if 40% of event must come from this scenario here, and only a few percent can come from here, then about a 37% might likely come from this scenario here. So this might be a major contributor of Chandrasekhar mass explosion, and that's what I'm focusing on. Okay, so what we recently do and we did this investigation, which got published in Astronomy and Astrophysics in July, was basically the simulation of the whole progenitor phase, so the whole evolution from the onset of mass accretion until the explosion of a series of accreted wildlife model, and we explore like the different impact of the composition of mass of the accretion material, accretion rate, nuclear reaction rate, and see really what's happening there. So what you have here we see on the left-hand side here is the so-called Kippenham diagram. So just to give you an idea of what the hell are you seeing here, you start with you're seeing basically on the vertical axis is a so-called mass coordinate. This is not a geometrical, let's say, representation. It tells you if you have your star, this is the center of the star, this is the surface, and this number here tells you how much material is underneath you if you are sitting in that point of the star, right? So you take your chair, you sit here, this tells you that there are open and solar mass material underneath you, okay? On the horizontal axis is the star, okay? So this tells you essentially how the structure of the star looks like at every single point in time. So this is a time evolution star structure. It gives you an overview of what's happening there. So what you have in both cases here, for example, you have the initial wildlife with initial mass of more or less 0.9 solar masses, right? And you have the accretion phase here. You see the mass is increasing is marked by this this light blue line. And then you see there's some point, a different point here and here. You see there's something going on here. So this circle here basically marks the presence of convective zone. And you see that something is happening, some nuclear burning is happening at the surface, and it really triggers the source of this convective zone. And so if you zoom in here, you see there are many of these events. Like in this case, we have 15 of them. So there are all these events, these flashes of carbon burning on the surface that takes place before the final explosion. That happens like more or less here after the so-called simmery phase. The carbon burning gas in the center drives the formation of this huge convective zone, which is called the simmery phase, and the final explosion happens. So before this happens, if the accretion rate is high enough, so beyond 2 × 10⁻⁶ masses per year, you can have carbon on the surface before it does in the center. Okay. And the way it happens is visible here. What you have here is the temporal profile of the wild dwarf, or the primary wild dwarf, from the surface to the center at different time of the accretion phase. So you have in red the temporal profile as a function in this case of density, which is a proxy of the internal position in the wild dwarf. In red you have the temporal profile when the wild dwarf is basically the total mass of 1 solar mass, then 1.2. So this tells you more or less as the accretion goes on, the mass increases. So this is gives an idea the time evolution of the temporal profile. You see, in this case, so the only difference, I forgot to say, the only difference between these two models is the accretion rate. This is a relatively low accretion rate, just in excess of 2 × 10⁻⁶ solar masses. This is more or less twice as much. Okay. The result is that you ignite carbon at the early time. In this model, you see that as the accretion goes on, this peak temperature here, which corresponds to the base of the accreted material, increases, and this peak is basically dictated by the compression heating of the clay material and the diffusive time scale to the internal of the wire, given that by the transition electrons. As the accretion goes on, this peak increases until he exceeds 1 gigakelvin, and this pretty much marks the ignition of carbon of the surface. Okay, and this also leaves a very distinct imprint into the HR diagram. You see here, you have in blue basically the low pressure rate model, instead in light blue the high pressure rate model, and each of these flashes leaves in the HR diagram this distinct flashes, goes up and down, very similar to what happens in the eject phase, but flipped over, since you don't have an envelope that expands and cool down, but you just have a bare pressure object that just leaves you the increase in temperature there. So you have what happens here. So that's key, because basically the reaction that drives the carbon burning on the surface is so-called is the fusion of two carbon 12 nuclei that release an helium-4 nucleus that then can be recycled and covered by the abundant neutron-2, which is the legacy of the previous GP phase, and can release neutrons, which we'll see. These are really key in producing then element beyond that later on. Okay. Oh, now I like to I like to focus on this very first step, because that's quite key. Because when carbon ignites here on the surface, you see there is a huge what looks like a huge convective zone, which actually is not really a convective zone. It's more like a flame propagation. It goes down. So what you see here, basically, there's something that appears in all our models. In this case, I just show you which models are here. But the reason why this is important is that there is this flame propagation, depending on the physics you put in your model, may or may not proceed all the way to the center and transforming your chemistry water into an oxygen neo-magnesium water, which will not explode the top of the supernova. In this case, this does not happen. The reason is realizing the way we treat convective mixing at the boundary between convective zone and radioactive zone. Essentially speaking, is in one of the models, the most popular way to describe convection is adopt the so-called Schwarzschild criterion, or the Redoux criterion if you also care about chemical gradients, which tells basically what you do. You take your temperature gradient in your stellar zone, you compare it to the adiabatic gradient. If it's in excess, the code tells you this is a convective zone, this is not. So you have some sort of discontinuity. And if you only apply, let's say, the pure Schwarzschild criterion, you have like a step behavior of the mixing. Now, this is not realistically what happens in a study. Will be more a situation of a shock propagation, if you like. What happens in a study, you have like what we know from multi-dimensional simulation. You have like a fast but not really a step function decrease of the mixing coefficient or the mixing efficiency, which goes down like this in exponential. It may be also exponential, but this means that there is some mixing going beyond the convective boundary a little bit. And these are some consequences. So you see here the propagation that the flame propagation as carbon ignites on the surface propagates toward the inside of the wire dwarf. You see here the temperature peak and the convective velocity. You see that you have really this convective zone which don't go all the way to the surface, but they are transported with the flame. So this tells you these are flame propagation. And most importantly, what you see here is that as a flame propagates, you have a fully convective zone here, a radioactive zone here, and in between there is a, let's say, partial mixing zone. In this place here, the burning is happening here at the top, where the peak temperature is. And what happens here is basically this partial mixing zone mixes some material from the already burned down material here, which is pouring carbon, which because it's been already burned out. It mixes with the carbon-rich material in front of the flame, lowering it down. And this makes And this process, which is repeated as the flame propagates, makes the carbon right in the carbon abundance right in front of the flame lower and lower and lower. In fact, you see the carbon profile in front of the peak temperature presents a plateau. If you don't allow any mixing beyond this virtual boundary, you'll see this increase here, which basically will compensate the decline of the temperature. Instead, it's this plateau, which basically means the propagation harder and harder as the flame propagates inside. And this actually prevents the flame to reach the center and maintains at least the most of the internal side of the wire carbon ridge, which is the key requirement to ensure explosion at the end of the evolution. So in this regime also it's quite a well-known thing that you need really some good radiometric resolution. Like according to the work of early 90s by Kins and colleagues, they estimated a resolution of about 1 kilometer. Well, you see here that resolution is quite high, especially at the region around the temperature peak. Like this is a kilometer, and we have 50 plus zone in it. Even in this part here, in the far away from the peak, resolution is of the order of 500 meters. So that's something well resolved, and we are happy with that. Okay, so this is the first event. As we saw before, then as the accretion goes on, you have a series of these flashes, and something very interesting happened here. And I want to show you here. So what happens here, this is like I'll just tell you what you're looking at right now. So in the vertical axis, you have the abundance of some key elements I'm showing here in terms of mass fraction. So this tells you really the abundance of how the percentage of the material composed of a certain element. Okay. In the x-axis coordinate, you have the mass coordinate again. So the center of the study is here. The surface is there. So here you have some key elements, some light elements to give you an idea of where we are: carbon, oxygen, and silicon. So carbon 12, oxygen 16, silicon 28, and also some elements way heavier than iron, in particular krypton, zirconium, barium. So what happens here is that as a carbon ignites, you have the pre-propagation. You see here that there's a lot of silicon down there, and then you see you have this flash. These are all these like sudden increase of these transition elements are flashes, are carbon flashes, which release alpha particle, which are then captured by neutrons too, and release neutrons via the neutral fine reaction. These neutrons are then captured by iron seeds, and like I don't know, like Lego bricks, you know, you have one after the other, and you form some stable element that decay, and you can synthesize from iron all the other elements up to a certain limit. But in this case, we show that you can really synthesize very efficiently elements heavier than iron, between iron and roughly zirconium. Actually, also a bit more than that. And also the physics is quite hard. For example, this is more or less the solar composition, more or less. You see, in the case of krypton, in this case, you have an overproduction of almost a factor of 1,000 compared to solar. What is this is zirconium, and also strontium is not there, but that's very efficient. And this happens over the most external 0.1 solar mass, roughly. Okay. So just to show you a bit more in detail what happens here, there is a Kipling diagram of these flashes that of which we saw a specific case in action. Again, this is a mass coordinate. This is accretion going. We see how the accretion proceeds. When the carbon ignites on the surface, you have the accretion and the flash, which drives the formation of a convective zone. Accretion again, flash. So you have this B value here. Well, and here you have the same diagram I showed in the movie. That is abundance of a chemical element as a function of the space coordinate from in the external layer. This is about this abundance here is about this pulse here, while this one is about this one here. So I'll show you just an example through these several pulses, and you see when carbon ignites, you have a huge peak temperature of the order of between 1 and 2 gigakelvin. This is basically where you activate the emission of alpha particle in the 12N. You see there is this step function here in krypton. This marks this is where really the production is really taking place. And you see how here this is this sync, the sync profile of the carbon-12 is where a previous flash up and left a carbon core region. This diagram is the same, but relative to these other parts, you see that many flashes happen, and you have another flash here, or the order of the temperature I told you, I just told you. Now, of course, it was well, since we know that the key reaction is taking place, you also want to test the impact of the uncertainty still affecting the secure reaction. This is like a very important reaction. It doesn't only take a role in this scenario, but is a well-known source of neutrons for the synthesis of elements beyond Earth in the galaxy that takes place in many other stellar sites, namely massive stars in the late space, also low mass stars with the giant branch phase. That's also a reason why the people are really investing a lot of money in measuring it, since today we have different estimation of this reaction, different by not by 3%, by a factor of 2 or 3. And depending on what choice of this reaction you stick in your code, you have quite different results, different by more or less by a factor of 2.4. This is what, for example, in light blue here, light blue diamond, that's the result you get using like a reaction rate dated 2021 by Ardsley, while what you get in the green is the result you get using the reaction rate given by the group in Notre Dame by Michael Fisher et al. In 2 years later. You see how this differs. So that has an impact which is really visible, and that's also why there's still an ongoing data measurement up in the Gran Sasso by the Luna collaboration, and this is financed by the ERC Stalingrado Shades by Andreas Best. Okay, so far so good. So we observed this distribution here, this distribution of chemical elements we saw before. And then we say, okay, which I don't want you to look at every single number, but let's give you an idea. It's like the output that are present in the paper we publish. So we produce 5 different heavy element distribution, actually not heavy element, from oxygen down there, that you can obtain assuming different starting conditions, different physical inputs at the beginning. So we presented 6 of them, 6 like a final chemical distribution at the end, just before the explosion. And then we want to test, since we eventually were really interested in seeing, in checking if these elements are eventually ejected in space or not. We basically tested this hypothesis by taking an explosive model by Townsley 2016, modifying it by putting on the external 0.1 solar mass layer one of these distribution. We took this one, and we put it we put this initial composition on the 0.1 external solar mass external layer, and we let it explode. We recopied the explosion as they copied it. And indeed, what we found was that there is really a bunch of elements between gallium and strontium, which are ejected in quite high abundances, like just below 10 to the minus 5 solar masses. Now, keep in mind, for example, I think that some of you might remember that the first time that heavy elements were detected from a kilonova, from the merger of 2 neutron stars. When strontium was detected, there was it has an abundance of more or less 10 to minus 5 solar masses. In this case, well, we have a series of elements in pretty much all the order of that. We have more or less 7 to the minus 6 solar masses of krypton, about 2 times minus 6 solar masses of strontium or rubidium. So that's quite interesting. That's one case. From this publication on, I also computed more distribution where you also get higher amounts of strontium. So the question is, could the ejection of this material constitute a new observable smoking gun of a Chandrasekhar explosion? So can we use maybe the spectral identification of these elements to distinguish a Chandrasekhar from a sub-Chandrasekhar explosion? So that's a long-term question I'd like to answer in the future project. Also, quite interestingly, if it allows me, I might spend 10 minutes later. Oh, okay.
Yeah.
Very interesting. Yes, for me, on top of that, we also noticed something, another very interesting thing, which is that in addition to heavy radioactive elements, also some interesting short-lived radionuclides, some unstable species are ejected. In particular, you see in this case, there is a high amount of iron-60, which is increased by more or less 20-fold compared to cases without the pre-supernova transacceleration enrichment. And again, also this is like a certainty observable that could be checked by, for example, next generation gamma ray telescopes, which will have the potential to detect single supernova remnant directly and see if you get iron-60 and at the same time non-luminosity-6. So this could be in type 1a remnants, so it could be a nice thing to check in addition to that. Okay, so also one last thing is that this was not the first time that we checked the full nucleosynthesis during the progenitor phase of a type A. In this work, we focus on the double degenerate fashion to produce an initial Chandrasekhar explosion, but in 2020 I did something similar, but focusing on the initial Chandrasekhar event explosion, a progenitor, sorry, forming from the hydrogen accretion event, which is the other way you have to form a Chandrasekhar mass whirlpool. Also in that case, we found a transdermal distribution, this time not stopping as zirconium, but going all the way to lead. Okay? So the key message is, doesn't matter really which way you produce a Chandrasekhar whirlpool, independent from the evolution scenario, you should get a transdermal element distribution. Only in the initial explosion, and as far as we know, not from a sub-Chandrasekhar. And the merits of that are the short timescale involving in sub-Chandrasekhar cases to produce this kind of distribution. So this is why this could be a format called neutron explosion versus sub-Chandrasekhar explosion. Okay. So basically, coming back to this pipeline, we did this step, and now, well, you know, the ball passes to the other simulation. So that's why I will visit Heidelberg this weekend, going there and discussing this step. Right now, also before doing this step, I'm in contact with Stuart Sim, because we are doing like a pre-check before doing, you know, expensive multi-D hydrogen simulation with 1 million percent particles. We are testing. I gave to Stuart like a grid of 8 in initial composition, from the most optimistic to the most pessimistic, and we want to check if we assume that the explosion of the whirlpool doesn't really process the external layers, which is reasonable because the you know, if you think about the deprivation, the standard deprivation from the center, you have some high peak temperatures in the center, and then the peak temperature goes lower, and eventually in the external layer we have peak temperatures between 3 and 1.5 gigakelvin. Then might not really significantly alter the composition there. It changes by some 10%, but assuming it doesn't really drastically modify it, by simply taking putting on top of the already competent multi-time element explosion, what I get here, can we get some significant observables? And even in the case that I provide, and if so, maybe you see it might really worth going here to the annual model, combine nucleosynthesis and compute the observables, which then will be really key in comparing with the tons of data we get in the next decade or so. Okay, so this is summary. Thank you. So As I showed you, as I was slowly merging carbon by the model for the Chandrasekhar mass, what happened is carbon burning nice on the surface before it does in the center, so triggering the emission of helium-4 nuclei and the neutron fan reaction, and therefore the emission of neutrons. Now, as a consequence, large production of transition elements in the outermost, some 10 to minus 2 solar mass to something in excess to 10 to minus 1 solar masses are established. And something similar happens also in the case of Chandrasekhar wide dwarf from the hydrogen accreting system, so as shown in Battino 2020. In particular, there are some elements like crystal rubidium stones produced by more than 3 orders of magnitude compared to solar, as well as some later species from between gallium, and also these species like gallium, germanium, selenium, crystal rubidium, and strontium are all ejected in high amounts, so in excess of 10 to minus 6 solar masses. Again, key question is, can we use this as a new observable? Could we find a new observable smoking gun watching the explosion? It's highly possible that these elements from type 1A can only be produced by neutron second event. And so this could be a new way to constrain the progenitor and distinguish between sub and neutron Chandrasekhar events. So of course, synthetic spectra from Alice transfer for this one. And the question is, can we, once we get the spectra, synthetic spectra, can we see this? And well, that's quite a good time to do this, because the great deep and all sky surveys are about to start, especially at SST for most types. And last but not the least, again, INO 60 in this case is increased by a factor of 20 compared to what is obtained without following the synthesis before the explosion, which is very, very common. And so this could be also a potential good case for next generation gamma ray telescope. And as I said, also this has been published in Astrophysics in July, so you find all the details here. Should you be keen to see that? And I think that's most important.
Ci sono domande? Do you have any question here? Stop sharing. Down in chat.
I can see that there's no
No questions from there. Okay.
Yeah, thanks. Umberto, very nice. So you showed us slow accretors. My question is on fast, rapid accretors, because well, so that you can even introduce another class of objects which are rapidly accreting by dwarfs. So my question is, the situation is still the same? Do you confirm the models you published in the past? Are there news about these models? And how many of these systems do you expect?
I mean, accretion or carbon?
I mean, the rapidly accreting for the nucleosynthesis.
You mean that we have the same set of?
Yeah.
These are other accreting while.
Yeah. Okay.
Yeah, no, in patterns, the second model. These are unrelated one. So you have video flashes established there. And as is described in that paper, the problem in there is, at least for some model, the accretion efficiency is quite low. And in 2020, which is the published model is 2017, in the 2020 paper I published, I tried to estimate the absolute minimum mass not to get the Chandrasekhar mass accreting hydrogen by simply integrating the mass increase profile during integration, assuming the highest possible companion star, so that it was later than the companion. And you cannot be the Chandrasekhar if you don't start from 0.9 solar masses. And Also, if you start from lower mass, not only you don't have enough material to get there, but also around open end, the mass detention is negative. So it's a bottleneck. So it must really be about that. And from that, if you check the number of, there was like a survey by Umberto in the 2020 something. They just checked the mass distribution of 1/40 parts of the radius of Earth, and more or less what they get, the number of water from in excess of 1 solar mass is about 3%, and more or less the same percentage between 0.9 and 1. So more or less is a 5 or 6% of these objects are there, which is consistent with the estimation that Johannes of the 16 did about the contribution of hydrogen accretion to the Chandrasekhar explosion. And what it really was something different. What it really was, they assumed that all the type 1A came from hydrogen accreting progenitors. And if that's true, you expect some sort a level of ultraviolet background from this, hot accretor. And then if you compare with the actual emission you get from Earth-like galaxies, that is consistent with more or less virus. So there's quite on the observation, it looks to me is quite strong. And the extension increases if you go lower thermicity. So it might be that earlier epochs, in my research might be strong. And it's something we have some observational data that support this, that of course the fraction of polarity contributing to the total array changes over time. So it's not fixed.
Okay. Thank you. This is not good. This is not good.
Not good.
It's not good because if you assume that this object can be standardized.
No. No. It's strange. There's a recent publication by a Korean people, very interested. They show that it's kind of flip the distribution between one go from young population to population, and they say they lose a balance.
That's a problem.
That's the problem. It's also interesting though.
Yeah, of course. So you can put again the presentation.
Yeah. This is the paper, by the way. It should come up.
Yeah. You go back to the slow down slides.
Slow down slide.
One. Back.
Not back. Okay. You can move.
The slow down accretion. The slide with the slow down accretion.
With the slow down accretion. This one. Okay.
I am one of the other stuff. I consider it not much interest. First economy. The reason why it goes on the left and not on the right in flash.
That's why it goes. The reason is that you don't have an envelope that expands and pull down, but you have the general object, so you see the direct bits of text. Yes.
It is the trend. So if you increase the mass, the radius decreases.
Exactly. Yeah. Exactly.
And during the flash, we go a bit on the red and then come back once again. The other panel, I never noticed that before. You have a density inversion.
Underpinning, yes, and that's something we saw. You mean this dip here? On the surface, you have a density. You mean here? Oh, yes, this here. Actually, this is something I overlooked.
That's good. So,
Yeah.
Oh,
And I overlooked the detail. Yeah. Yeah.
probably we never ever looked
No,
at that.
no.
That's-
I was focused on this.
Yeah.
And my eye were here. Yeah. Really ignored.
Yes. You density inversion.
is quite close to the surface. So
Yeah, it's all here.
but again,
I'll come back to it.
just to understand.
Yeah.
And the other comment is that the production of iron 60 is related to the neutral
Yes. Yes. Yeah.
and this is the reason why we have the same in the massive stars.
Yeah.
Stars. And we found in
The same numbers, more or less. Just so that all
more or less have the same because you at any temperature you remove that reaction. It's more or less the same amount of neutrons at the same time. And it is exactly the same also in helium-active models.
okay. Okay.
So we find exactly the same. And so the point is that if you can find the print of iron 60 in a supernova, and then you have an evidence of something which has the activation.
So exactly. That's
Yes.
that's it.
But in general, you can kind of wrong.
Yeah.
So because, but it is interesting because in any case, you have the print of that also.
Yeah. You saw that relation is active. Yes. So the noodles flow. Yeah. That's what.
And the other point is that considering the contribution coming to the building of different channels, after 20 years, I'm convincing myself that the scenario is more on the direction side.
I agree. No, as I said earlier, I think there's my gut feeling there's a normal channel,
Yeah.
but you need more than one.
Yeah.
To get the line to the spectra. So when did you see? So you have too much many things.
But all models requires massive weight load.
Yeah.
This is the problem you mentioned just 2 minutes ago. And I don't see any evolutionary path driving the formation of massive weight load.
Yeah, no, that's I agree that double evolution is the dominant. I see. I'm not saying that this is dominant, but it is.
Is that when you say in detonation or double detonation, you have overproduction on titanium, and so on. But this depends on the mass of the bound. So if you have a massive weight dwarf, you have a small bound. In this case, the production of radioactive carbon is larger than used.
I need to check this up because these numbers were taken from the paper of Fiontan.
Yeah.
I think they tested variety of condition of carbon core and matter. And when they did the GC simulation, I think there's a distribution of population of this condition. And they found that result is I need to see the assumption I made, but they assume a distribution or at least disposal of this condition, and that was the result.
Because you reported the initial mass with your 0.01 to 0.1.
Yeah, I mean they assume an INAF and they solve it for the next.
But if your weight dwarf is massive enough, the buffer is very small. You are at 0.02, 0.03. In that case, the overproduction of chrominal magnetic is very small. So you don't have that problem. The classical problem with the detonation models.
So you're saying that the double detonation model they included were also peculiar component, not the standard one.
Yeah.
Yeah.
In principle. I have to read it again.
Okay, so thank you, Umberto.
Yeah.
Thank you for your attention.
Next time is in 2 weeks.